In this example, I am going to be using the Central Limit Theorem. A quality control manager believes that the mean life of a cell phone battery is 36 months with a standard deviation of 3 months. If she is correct, what is the probability that the mean of a sample of 70 cell phone batteries would differ from the claimed population mean by less than, oops, I forgot this value here, 2 months? All right, so this quality control manager is making a claim about the population of cell phone batteries. She is claiming that the average life for the population of cell phone batteries is 36 months and the standard deviation is 3 months. If this claim is true, let's find the probability that out of a sample of 70 cell phones, so in this sample n is equal to 70, that the batteries would differ from the claimed population mean by less than 2 months. All right, so we want this difference to be less than 2 months from the claimed mean. So in terms of a sample mean based on a sample size of 70, this is finding the probability that X bar is between 34 and 38. Because if we want to be less than 2 months from the claimed mean, less than 2 months below the claimed mean would be 34, and 2 months above the claimed mean would be 38. Now, this is a probability corresponding to a sample mean, so I need to use the Central Limit Theorem. The Central Limit Theorem kicks in for any distribution if the sample size is at least 30. So we have that condition met. We need the mean and the standard deviation for the distribution of the sample means under the Central Limit Theorem. Mu sub x bar is the same as the original population, so the mean of the sample means is the same as the original. The standard deviation of the sample means is the original standard deviation of individual value, that distribution, divided by the square root of the sample size. So the mean that we need to use our technology for will be 36. That's the same as the original population. But the standard deviation for the distribution of the sample means is always smaller. Specifically, it's smaller by the amount sigma over the square root of n. So that's going to be 3 over the square root of 70. So we can get a decimal approximation here, or I like to put this entire expression into my calculator for the standard deviation. Okay, so we're finding the probability X bar falls between 34 and 38. So looking at that as a shaded area under the bell curve, because the Central Limit Theorem says that X bars will be normally distributed, the mean is going to be the same as the original population. And I want to go from 34 up to 38. Now this might not be shaded proportionally correct, so I'm just treating this as a visual aid. And going back to our probability statement, if you want to standardize and use the z-table, as I've said in my previous examples, you would have to convert both of these endpoints to z-scores by subtracting the mean and dividing by the standard error of the mean. I'm going to go ahead and use the calculator for that. So going to my normal CDF menu, let's try to fit this in here. My lower bound is going to be 34. My upper bound is going to be 38. The mean is 36, and that standard deviation is 3 divided by the square root of 70. All right, so I get a fairly high probability here. I'm going from 34 to 38, lower bound, upper bound, mu, and sigma. Okay, so most of the cell phone batteries should last within 2 months of 36. Okay, and that is actually a good thing. So if I rounded to 4 decimal places, I would be rounding to 1, but this is not an absolute probability. Okay, so I would leave this as the probability is approximately 0.9999 and leave it at that. I probably chose not very good numbers here and here. I find that students tend to either round up to 1 or round down to 0 depending on the problem. But remember, a probability of exactly 1 represents a probability of an event that occurs absolutely, and the probability of 0 represents an event that is an impossible event, and neither of those cases hold. So this probability is very close to 1, but it's not exactly equal to 1.